Hello everyone, I'm back with another video. Today I want to talk about more in detail about the network prediction plugin. So let's start with what is the network prediction plugin. So the network prediction plugin is a tool that will allow Unreal Engine developers to make high quality, very responsive, competitive multiplayer games. This plugin will allow you to build logic for multiplayer games without having to worry about the multiplayer logic portion of it, like replicated properties and RPCs. This plugin was in the engine for a few years, but it seemed as it was not supported anymore. But now, with Mover 2.0, it's being built with it, which means that the implementation of the plugin is worthy to build on it the next generation of network movement in Unreal. The plugin itself has a very robust implementation of network prediction and rollback, but is missing a couple of few steps to finish, just a couple of more steps to the finish line. And this didn't sit right with me, so I did my best to try to finish these last few features and help the plugin reach the finish line. So let's talk about the missing features, and we'll go through them one by one and the results of the implementation that I did. Number one from the missing features is smoothing. Number two is high bandwidth usage. Number three, it's high input buffering. And number four is replay. So these are what I believe are critical features that the plugin needs for it to be the best it can possibly be. So let's start with the first one, smoothing. There's two types of smoothing. There is fixed tick and there's correction smoothing. So for fixed tick simulation, it's it means that the simulation ticks at a different rate from the render frame. So your simulation can tick at 60 frames per second, but you are rendering at 144, 200 frames a second. For the independent simulation, your simulation ticks at the same rate as your render frame. So you can tick differently, different speed than other client does, than the server does. So fixed tick is preferred for network games because the simulation is predictable and the simulation is consistent. So giving the same input and same input states, it will always give you the same output state because it's the same delta time. But this brings us to smoothing for fixed tick and smoothing for corrections. Smoothing for corrections is the simplest that there is. When a client and the server disagree, the server is going to ask the client to correct itself. And currently, when a correction happens, it's teleportation. So the client will get teleported to the correct position. This is jarring and it could make minute and minuscule corrections that with smoothing wouldn't be noticeable at all become very noticeable as jitter and teleportation of the player. So these are the two types of smoothing. Now I implemented this in the network prediction plugin by default as it was intended because the original author had this in mind. So I finished it along with changes that I did to Mover. Okay, so to implement this code and implement smoothing in Mover itself, because the network prediction plugin is a generalized framework for this kind of stuff. And the implementation that I did was in the sorry, in the generalized framework, and uh, it means that each simulation will need to have some kind of functions that it needs to be exact, it needs to three functions, get delta, apply delta, and scale for each sync state of the simulation, and a function called finalize smoothing frame in the driver itself, example, the mover component. So these things implement smoothing and allows the character to tick at a fixed rate which is the same on the client and on the server, and the render frame to be however whatever the client wants with complete smoothing. So uh, to showcase this, you can see I have a client here, and you can see how the capsule is moving. I don't know how much of this will be visible in the video with lower frame rate, but the you can see the capsule is teleporting, but the character is very smooth because the mesh is being smoothed out. So that's smoothing. The number two thing that I would like to talk about is bandwidth optimization. So if I go here, let's make sure that we have it turned off, np.bandwidth optimization, and let's set it to 0. So, and let's do a little profile. Let's put 2 players. So the one that I profile has a simulated proxy. So I'm gonna profile this guy. Net profile enable. So he has one simulated proxy, one autonomous proxy, which is himself, and then the server. Let's end it. Uh, and let's take a look at it. Uh, this is the time, the file. So you can see that these two, the replication proxy, autonomous and simulated, are the two properties that the network prediction uses to funnel its data through the network system of Unreal. So all the data related to network prediction, the state, the inputs, everything uh, is being it uses this along with an RPC. You can see server receive client input to send the input from the local player to the server. Uh, this is from the server to the local player. So this is from the server to the local player for autonomous, and this is from the server to the simulated proxies. And you can see that the simulated proxies are sending more because the autonomous are only getting the state, and the simulated proxies are getting the state and the input, despite them being interpolated. So they don't actually use that input for simulation, but I assume you might want to query the input on simulated proxies at some time. So the the actual implementation of the bandwidth optimization, it's the setting is given to the states of the simulation, but it's up to those states to decide what they do with it. So what do I mean by that? In the function net serialize function, you will get a setting telling you who is the target of the simulation, whether this is being sent to simulated proxies, or the simulated proxies are reading it, or is it being sent to autonomous. So the target of this replication, and you can check if it's simulated, for example, like here, mover types. So example, we have these net serialize for the input collection. So in the net serialize function, we are checking if we are simulated proxies, we're doing net serialize simulated. And if you go to this f character default input, which is the struct, sorry, which is the struct that actually has all the inputs, you can see that I did override net serialize simulated. If you don't override it, it won't do anything. It will just use net serialize. I did override it, and I didn't add anything. I'm not serializing anything. Simulated proxies do not need to be sent input. You can add the input you really need to query to be serialized here, but you can just leave it empty. And now when you do leave it empty, you will actually notice a difference. So if I go np.bandwidth optimization and turn back on, make sure that's on, and I play, let's turn on that profile. Okay, disable, and let's look at it. 1404. And you can see the simulated proxies are right now 360 compared to 460. This is the average size. So there is at least 100 bits that is being saved on the simulated proxy. And remember that for every player there is multiple simulated proxies and one autonomous. So if you have 10 players in the game, 4 teammates, uh, uh, 5 teammates, 5 enemies, for example, that's 10 of these simulated proxies. So 100 bits for just sending the input, for not sending the input that you're not actually using, is a big optimization. That is about 25% of the entire packet. And a lot more can be reduced. I didn't really go through all of the things, but in the state of the mover itself, a lot more things can be like reduced. Like for example, layered moves. You might not need the start time of the layered move and the current time of the layered move. For example, you only need for double jumping layered move. You only need the number for simulated proxies. Like how many jumps, what number of jump I have, and how many jumps I have left. For example, you don't need to know all of the other data that the server and the client, the actual local player, are communicating between each other to keep everything in sync. So let's turn that optimization back on. Um, and this bandwidth optimization, I just added this right now for the sake of the video. It will obviously not be there and it will be on by default and cannot be turned off. Uh, so we talked about the serialization. So let's talk about the third thing, which is client-side time dilation. So the first thing I'm gonna do is to make this simpler. It's one player, and in the console command, I'll go np dot time dilation disable, and for reference, I have about 150 ping. So in and out between 80 and 50, so together it will be about 150 ping. So let's look at this. These are the buffered commands that the server has. This is the Network Prediction Insights plugin. Uh, so these buffered commands are what the client has sent to the server, and the server is still did not reach those commands yet. He's uh, he's buffering them, and he will consume them one by one in time. But this is a problem. The more these exist, it's like induced lag between the client and the server. The bigger this is, the the longer it will take for the server to reach the state that the client has reached, and it also means it will take longer for the server when he reaches that state to send it to other players to see. So this will induce lag for other players. You'll be behind for other players, and you don't want this. And obviously, this is something that the original author of the plugin knew about, and you can see that he had it to do. We should have something to bring this back down, which means skipping frames. We don't want temporary poor conditions to cause permanent high input buffering, and that's what's actually happening. So we don't necessarily mean that you're gonna skip frames, because if you use time dilation, you will use all the frames. You just ask the client to tick a little bit slower, and thus sending input in a slower rate, so it allows the server to eat the input that they have in the buffer faster. Uh, like before, faster than it gets new inputs, and thus making it smaller. So if we turn it on, np time dilation disable and we set it to 0, so do not disable it, and we turn it on, you will see the final state is 2 inputs being buffered and there is no corrections. I think 150 ping with 1 packet loss is a very, it's the common thing you would have. I can increase this to 5% for in and out. And you can see it's a steady 1-2 frames buffer. And when it ever happens that you have a packet loss, you just duplicate the input that you used last frame, and it's highly likely that the player would have held the same input between one frame to the next. It's 16 milliseconds for a frame. We're humans, I don't think we can do that. I mean, when you do switch another button, there will be a change from one frame to the next, but most of the time we are holding it, and the server will assume that that's one extra input that has been created. It will not override your input when it receives it, but it will assume it's one extra input. Uh, it doesn't usually cause corrections because it's a really small distance. But if it happens multiple times, then it will cause a small corrections. But you can never see that corrections because of smoothing. But now, as you always notice, whenever I stop, it will stop at 1 or 2 frames buffered. And that's time dilation. And this is how you keep your state that you have here as close as possible to what the other players see of you. So there is not too much discrepancy. Um, so that's about time dilation. And number 3 is replay. So the network prediction plugin, when you try to do replay by default, it just crashes because uh, the replay implementation was started, but I don't think it was tested. So there was a small things that needed to be done to it for it to work, and now the replay works. I have this game instance that I have in this project already set up, so to start a replay with buttons, so I'm gonna press 1 and start a new replay. Jump for a bit, run around, and then I'll press 2, stop the replay, and 3 to play it. And here's full replay support on the network prediction plugin. And I even stopped in the middle of the pose. So with this, I think the network prediction plugin is fully complete. It's feature complete. There's a couple of few things I would like to do. One last feature I would like to add is lag compensation in the network prediction plugin, so you can rewind actors, uh, bunch their simulations together. So if you have like an ability simulation and a movement simulation, they would be given together as the global state of the actor in the network prediction. And one last thing is a cleanup where I want to remove all the physics code from the network prediction plugin because it's dead code. It should not be used. It's not fully implemented. It's not fully done, and it will never be fully done. And there is already chaos network prediction physics, which if you want to use physics for network prediction, you should use that system. So the physics here will not work. So let's not leave the code there. It's unnecessary. So that's what I'm thinking. Maybe cleaned up all that code. And yeah, that will make things a little bit clearer to read in the source code if there is not so much physics related stuff. Okay, so that's enough of a rant of me. Uh, you guys will find the link to the GitHub repo for the fork of this plugin in the description. You will also find a link to the Discord server if you have any questions about the network prediction plugin or things like that. And thank you very much for watching, and I hope you have a great week. See you later. Goodbye.